Section 13 of the Chemistry of Cookery. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Chemistry of Cookery by W. Mattieu Williams. Chapter 12. Gluten. Bread. Having treated the cookery of the chief constituents of the roots and stems of the plants, the fiber and the starch, I now come to food obtained from the seeds and the leaves. Taking the seeds first, as the more important, it becomes necessary to describe the nitrogenous constituents, which are more abundant in them than in any other part of the plant, though they also contain starch and cell material, or woody fiber, as already stated. In the preceding chapter, I described a method of separating starch from flour by washing a piece of dough in water, and thereby removing the starch granules which fall to the bottom of the water. If this washing is continued until no further milkiness of the water is produced, the piece of dough will be much reduced in dimensions and changed into a tough gray elastic and viscous or glutinous substance, which has been compared to birdlime and has received the appropriate name of gluten. When dried, it becomes a hard, horny, transparent mass. It is insoluble in cold water and partly soluble in hot water. It is soluble in strong vinegar and in weak solutions of potash or soda. If the alkaline solution is neutralized by an acid, the gluten is precipitated. If crude gluten, obtained as above, is subjected to the action of hot alcohol, it is separated into two distinct substances, one soluble and the other insoluble. As the solution cools, a further separation takes place of a substance soluble in hot alcohol, but not in cold, and another soluble in either hot or cold alcohol. The first, that is to say, that insoluble in either hot or cold alcohol, has been named gluten fibrin. That soluble in hot alcohol, but not in cold, gluten casein. And that soluble in either hot or cold alcohol, gluten. I give these names and explain them, as my readers may be otherwise puzzled by meeting them in books where they are used without explanation, especially as there is another substance presently to be described, to which the name of vegetable casein has also been applied. The gluten fibrin is supposed to correspond with blood fibrin, gluten casein with animal casein, and gluten with albumen. Their composition is as follows, which I append for what it is worth in connection with this theory, but mainly to show how small is the difference between the chemical composition of the nitrogenous constituents of animals and those of plants. I shall come to this subject again. Displayed is a table of carbon, hydrogen, nitrogen, oxygen, and sulfur contents in gluten fibrin, gluten casein, and gluten. In gluten fibrin, there is 53.23% of carbon, 7.01% of hydrogen, 16.41% of nitrogen, and 23.35% of oxygen and sulfur. In gluten casein, there is 53.46% of carbon, 7.13% of hydrogen, 16.04% of nitrogen, and 23.37% of oxygen and sulfur. In gluten, there is 53.27% of carbon, 7.17% of hydrogen, 15.9% of nitrogen, and 23.62% of oxygen and sulfur. In blood fibrin, sharer, there is 53.57% of carbon, 6.9% of hydrogen, 15.72% of nitrogen, and 22.81% of oxygen and sulfur. In the animal casein, there is 53.83% of carbon, 7.15% of hydrogen, 15.65% of nitrogen, and 23.37% of oxygen and sulfur. And finally, in albumen, there is 53.50% of carbon, 7% of hydrogen, 15.5% of nitrogen, and 24% of oxygen and sulfur. Gluten is usually described as partly soluble in hot water. My own examination of this substance suggests that partially soluble is a better description than partly soluble, Miller, or very slightly soluble, Laymen. This difference is not merely a verbal quibble, but very real and practical in reference to the rationale of its cookery. A partially soluble substance is one which is composed of soluble and also of insoluble constituents, which, as already stated, is strictly the case with gluten, in reference to the solvent action of hot alcohol. A very slightly soluble substance is one that dissolves completely, but demands a very large quantity of the solvent. I find that the action of hot water on gluten, as applied in cookery, is to effect what may be described as a partial solution. That is, it effects a loosening of the bonds of solidity without going so far as to render it completely fluid. It appears to be a sort of hydration similar to that which is effected by hot water on starch, but less decided. To illustrate this, wash some flour in cold water, so as to separate the gluten in the manner already described. Then boil some water as in making ordinary bill stickers paste, and wash this in cold water. The gluten will come out with difficulty from this, and when separated will be softer and less tenacious than the cold-washed specimen. This difference remains until some of the water it contains is driven out, for which reason I regard it as hydrated, though I am not prepared to say that the hydration is of a truly chemical character, a definite chemical combination of gluten with water. It may only be a mechanical combination, a loosening of solidity by a molecular intermingling of water. The importance of this in cookery, of grain food, is very great, as anybody who aspires to the honor of becoming a martyr to science may prove by simply making a meal on raw wheat, masticating the grains until reduced to small pills of gluten, and then swallowing them. Mild indigestion or acute spasms will follow, according to the quantity taken and the digestive energies of the experimenter. Raw flour will act similarly, but less decidedly. Bread making is the most important, as well as a typical example, of the cookery of grain food. The grinding of the grain is the first process of such cookery. It vastly increases the area exposed to the subsequent actions. The next stage is that of surrounding each grain of the flour with a thin film of water. This is done in making the dough by careful admixture of a modicum of water and kneading, in order to squeeze the water well between all the particles. The effect of insufficient enveloping in water is sometimes seen in a loaf containing a white powdery kernel of unmixed flour. If nothing more than this were done, and such simple dough were baked, the starch granules would be duly broken up and hydrated, the gluten also hydrated, but at the same time the particles of flour would be so cemented together as to form a mass so hard and tough when baked that no ordinary human teeth could crush it. Among all our modern triumphs of applied science, none can be named that is more refined and elegant than the old device by which this difficulty is overcome in the everyday business of making bread. Who invented it, and when, I do not know. Its discovery was certainly very far anterior to any knowledge of the chemical principles involved in its application, and probably accidental. The problem has a very difficult aspect. Here are millions of particles, each of which has to be moistened on its surface, but each, when thus moistened, becomes remarkably adhesive, and therefore sticks fast to all its surrounding neighbors. We require, without altogether suppressing this adhesiveness, to interpose a barrier that shall sunder these millions of particles from each other so delicately as neither to separate them completely nor allow them to completely adhere. It is evident that if the operation that supplies each particle with its film of moisture can simultaneously supply it with a partial atmosphere of gaseous matter, the difficult and delicate problem will be effectively solved. It is thus solved in making bread. As already explained, the seed, which is broken up into flour, contains diastase as well as starch, and this diastase, when aided by moisture and moderate warmth, converts the starch into dextrin and sugar. This action commences when the dough is made. This alone would also increase the adhesiveness of the mass, if it went no further, but the sugar thus produced may, by the aid of a suitable ferment, be converted into alcohol. As the composition of alcohol corresponds to that of sugar minus carbonic acid, the evolution of carbonic acid gas is an essential part of this conversion. With these facts before us, their practical application in bread making is easily understood. To the water with which the flour is to be moistened, some yeast is added, and the yeast cells, which are very much smaller than the grains of flour, are diffused throughout the water. The flour is moistened with this liquid, which only demands a temperature of about 70 degrees Fahrenheit, to act with considerable energy on every granule of flour that it touches. Instead, then, of the passive, lumpy, tenacious dough produced by moistening flour with mere water, a lively sponge, as the baker calls it, is produced, which rises or grows in bulk by the evolution and interposition of millions of invisibly small bubbles of gas. This sponge is mixed with more flour and water, and kneaded again, to effect a complete and equal diffusion of the gas bubbles, and finally the porous mass of dough is placed in an oven previously raised to a temperature of about 450 degrees. The baker's old-fashioned method of testing the temperature of his oven is instructive. He throws flour on the floor. If it blackens without taking fire, the heat is considered sufficient. It might be supposed that this is too high a temperature, as the object is to cook the flour, not to burn it. But we must remember that the flour which has been prepared for baking is mixed with water, and the evaporation of this water will materially lower the temperature of the dough itself. Besides this, we must bear in mind that another object is to be attained. A hard shell or crust has to be formed, which will so encase and support the lump of dough as to prevent it from subsiding when the further evolution of carbonic acid gas shall cease, which will be the case some time before the cooking of the mass is completed. It will happen when the temperature reaches the point at which the yeast cells can no longer germinate, which temperature is considerably below the boiling point of water. In spite of this high outside temperature, that of the inner part of the loaf is kept down to a little above 212 degrees by the evaporation of the water contained in the bread. The escape of this vapor and the expansion of the carbonic gas bubbles by heat combine to increase the porosity of the loaf. The outside being heated considerably above the temperature of the inner part, this variation produces the differences between the crust and the crumb. The action of the high temperature in directly converting some of the starch into dextrin will be understood from what I have already stated, and also the partial conversion of this dextrin into caramel, which was described in Chapter 7. Thus we have in the crust an excess of dextrin as compared with the crumb, and the addition of a variable quantity of caramel. In lightly baked bread with a crust of uniform pale yellowish color, the conversion of the dextrin into caramel has barely commenced, and the gummy character of the dextrin coating is well displayed. Some such bread, especially the long staves of life common in France, appear as though they had been varnished, and their crust is partially soluble in water. This explains the apparent paradox that hard crust or dry toast is more easily digested than the soft crumb of bread. The cookery of the crumb, not having been carried beyond the mere hydration of the gluten and the starch, and such degree of dextrin formation as was due to the action of the diastase of the grain during the preliminary period of rising. In the crust, some of the work of insalivation is already done by the baker. The digestibility of toast is doubtless aided by its brittleness, causing it to be more broken up and mixed with the saliva. Everybody has, of course, heard of unfermented bread, and many have tasted it. Several methods have been devised, some patented, for effecting an evolution of gas in the dough without having recourse to the fermentation above described. One of these is that of adding a little hydrochloric acid to the water used in moistening the flour, and mixing bicarbonate of soda and powder with the flour. To every 4 pounds of flour, ½ ounce of bicarbonate and 4½ fluid drams of hydrochloric acid of 1.16 specific gravity. These combine and form sodium chloride, common salt, with evolution of carbonic acid. The salt thus formed takes the place of that usually added in ordinary bread making, and the carbonic acid gas evolved acts like that given off in fermentation, but the rapidity of the action of the acid and carbonate presents a difficulty. The bread must be quickly made, as the action is soon completed. It does not go on steadily increasing and stopping just at the right moment, as in the case of fermentation. Other methods, similar in principle, have been adopted, such as adding ammonia carbonate with a soda carbonate. The ammonia salt is volatile itself, besides evolving carbonic acid by its union with the acid. In spite of the great amount of ingenuity expended upon the manufacture of such unfermented bread, and the efforts to bring it into use, but little progress has been made. The general verdict appears to be that the unfermented bread is not so sweet, that it lacks some element of flavor, is chippy or tasteless, as compared with good old-fashioned wheaten bread, free from alum and other adulteration. My theory of this difference is that it is due to the absence of those changes which take place while the sponge or dough is rising, when, if I am right, the diastase of the grain is operating, as in germination, to produce a certain quantity of dextrin and sugar, and possibly acting also on the gluten. Deficiency of dextrin is, I think, the chief cause of the chippy character of aerated bread. It must be remembered that in ordinary bread making, the fermentation is protracted over several hours, during which the temperature most favorable to germination is steadily maintained. The practical importance of the fermentation is strikingly shown by the fact that in the course of sponge rising, dough rising, and baking, a loaf becomes about 4 times as large as the original mixture of flour and water, etc., of which it was made. Or otherwise stated, an ordinary loaf is made up of 1 part of solid bread to more than 3 parts of air bubbles or pores. French rolls and some other kinds of fancy bread are still more gaseous. So far I have only named the flour, water, salt, and yeast. These, with a little sugar or milk added according to taste and custom, are the ingredients of homemade bread. But baker's bread is commonly, though not necessarily, somewhat more complex. There is the material technically known as fruit, and another which bears the equivocal name of stuff, or rocky. The fruit are potatoes. The quantity of these prescribed in Knight's Guide to Trade is 1 peck to the sack of flour. This proportion is so small, about 3% by weight, that, if not exceeded, it cannot be regarded as a fraudulent adulteration, for the additional cost involved in the boiling, skinning, and general preparing of the small addition exceeds the saving in the price of raw material. The fruit, therefore, is not added merely because it is cheaper than flour, as many people suppose. The instructions concerning its use, given in the work above named, clearly indicate that the potato flour is used to assist fermentation. These instructions prescribe that the peck of potatoes shall be boiled in their skins, mashed in the seasoning tub, then mixed with 2 or 3 quarts of water, the same quantity of patent yeast, and 3 or 4 pounds of flour. The mixture is left to stand for 6 or 12 hours, when it will have become what is called a ferment. After straining through a sieve to separate the skins of the fruit, it is mixed with a sack of flour, water, etc. It is evident from this point that it would not pay to add such a quantity in such a manner as a mere adulterant. The baker uses it for improving the bread, from his point of view. The stuff, or rocky, consists, according to Tomlinson, of 1 part of alum to 3 parts of common salt. The same authority tells us the bakers buy this at 2d per packet, containing 1 pound in each, and that they believe it to be ground alum. They buy it thus for immediate use, being subject to a heavy fine if they keep alum on the premises. The quantity of the mixture ordinarily used is 8 ounces to each sack of flour weighing 280 pounds, so that the proportion of alum is but 2 ounces to 280 pounds. As 1 sack of flour is, with water, made into 80 loaves weighing 4 pounds each, the quantity of alum in 1 pound of bread amounts to 1/160th of an ounce. The rationale of the action of this small quantity of alum is still a chemical puzzle. That it has an appreciable effect in improving the appearance of the bread is unquestionable, and it may actually improve the quality of bread made from inferior flour. One of the baker's technical tests of quality is the manner in which the loaves of a batch separate from each other, that they should break evenly and present a somewhat silky rather than a lumpy fracture is a matter of trade estimation. When the fracture is rough and lumpy, one loaf pulling away some of the just belongings of its neighbor, the feelings of the orthodox baker are much wounded. The alum is said to prevent this impropriety, while an excess of salt aggravates it. It appears to be a fact that this small quantity of alum whitens the bread. In this, as in so many other cases of adulteration, there are 2 guilty parties: the buyer, who demands impossible or unnatural appearances, and the manufacturer or vendor, who supplies the foolish demand. The judging of bread by its whiteness is a mistake which has led to much mischief, against which the recent agitation for wholemeal is, I think, an extreme reaction. If the husk, which is demanded by the wholemeal agitators, were as digestible as the inner flour, they would unquestionably be right, but it is easy to show that it is not, and that in some cases the passage of the undigested particles may produce mischievous irritation in the intestinal canal. My own opinion on this subject, it still remains in the region of opinion rather than of science, is that a middle course is the right one. That is to say, that bread should be made of moderately dressed or seconds flour, rather than overdressed firsts or undressed thirds, that is, unsifted wholemeal flour. Such seconds flour does not fairly produce white bread, and consumers are unwise in demanding whiteness. In my household, we make our own bread, but occasionally, when the demand exceeds ordinary supply, a loaf or 2 is bought from the baker. I find that, with corresponding or identical flour, the baker's bread is whiter than the homemade, and proportionally inferior. I may describe it as colorless in flavor. It lacks the characteristic of wheaten sweetness. There are, however, exceptions to this, as certain bakers are now doing a great business in supplying what they call homemade or farmhouse bread. It is darker in color than ordinary bread, but is sold nevertheless at a higher price, and I find that it has the flavor of the bread made in my own kitchen. When their customers become more intelligent, all the bakers will doubtless cease to incur the expense of buying packets of stuff or rocky or any other bleaching abomination. Liebig asserts that in certain cases, the use of lime water improves the quality of bread. Tomlinson says that in the time of bad harvests, when the wheat is damaged, the flour may be considerably improved, without any injurious result whatever, by the addition of from 20 to 40 grains of carbonate of magnesia to every pound of flour. It is also stated that chalk has been used for the same purpose. These would all act in nearly the same manner by neutralizing any acid, such as acetic, that might already exist or be generated in the course of fermentation. When gluten is kept in a moist state, it slowly loses its soft, elastic, and insoluble condition. If kept in water for a few days, it gradually runs down into a turbid, slimy solution, which does not form dough when mixed with starch. The gluten of imperfectly ripened wheat, or of flour, or wheat that has been badly kept in the midst of humid surroundings, appears to have fallen partially into this condition, the gluten being an actively hygroscopic substance. Liebig's experiments show that flour in which the gluten has undergone this partial change may have its original qualities restored by mixing 100 parts of flour with 26 or 27 parts of saturated lime water, and a sufficiency of ordinary water to work it into dough. I suspect that the action of the alum is of similar kind, though this does not satisfactorily account for the bleaching. The action of sulfate of copper, which has been used in Belgium and other places for improving the appearance and sponginess of loaves, is still more mysterious than that of alum. Kuhlmann found that a single grain in a 4-pound loaf produced a marked alteration in the appearance of the bread. Fortunately, this adulteration, if perpetrated to a mischievous extent, may be easily detected by acidulating the crumb, and then moistening with a solution of ferrocyanide of potassium. The brown color thus produced betrays the presence of copper. The detection of alum in small quantities is extremely difficult. I should add that the ancient method of effecting the fermentation of bread, which I understand is still employed to some extent in France, differs somewhat from the ordinary modern English practice. When flour made into dough is kept for some time moderately warm, it undergoes spontaneous fermentation, formerly described as panary fermentation, and supposed to be of a different nature from the fermentation which produces yeast. Dough in this condition is called leaven, and when kneaded with fresh flour and water, its fermentation is communicated to the whole lump, hence the ancient metaphors. In practice, the leaven was obtained by setting aside some of the dough of a previous batch, and adding this to the next, when its fermentation had reached its maximum activity. One reason why the modern method has superseded this appears to be that the leaven is liable to proceed onward, beyond the first stage of fermentation, or that producing alcohol and run into the acidulous or vinegar-forming fermentation produces sour bread. Another reason may be that the potato mixture above described, which is but another kind of leaven, is more effectual and convenient. Dr. Dauglish's method, patented in 1856, 1857, and 1858, is based on the fact that water under pressure absorbs and holds in solution a large quantity of carbonic acid gas, which escapes when the pressure is diminished, as in uncorking soda water, etc. Dr. Dauglish places the flour in a strong airtight iron vessel, then forces water saturated with carbonic acid under high pressure into this. Kneading knives mix the dough by their rotation. When the mixture is completed, a trap at the lower part of the globular iron vessel is opened, The pressure of the confined carbonic acid above forces the dough through this in a cylindrical jet or flat ribbon as required, and this squirted cylinder or ribbon is fashioned by suitable cutters, etc., into loaves. The compressed gas expands, and the loaves are smartly baked before the expansive energy of the gas is exhausted. It is justly claimed for this process that it is far more cleanly than the ordinary method of making bread, as with suitable machinery, such aerated bread can be made without handling. The difference between new and stale bread is familiar enough, but the nature of the difference is by no means so commonly understood. It is generally supposed to be a simple result of mere drying. That this is not a true explanation may be easily proved by repeating the experiments of Boussingault, who placed a very stale loaf, 6 days old, in an oven for an hour, during which time it was, of course, being further dried, but nevertheless it came out as a new loaf. He found that during the 6 days, while becoming stale, it only lost 1% of its weight by drying, and that during the 1 hour in the oven, it lost 3.5%, in becoming new and apparently more moist. By using an airtight case instead of an ordinary oven, he repeated the experiment several times in succession on the same piece of bread, making it alternately stale and new each time. For this experiment, the oven should be moderately heated. 260 degrees to 300 degrees Fahrenheit is sufficient. I am fond of hot rolls for breakfast and frequently have them, a la Boussingault, by treating stale bread crusts in this manner. My wife tells me that when the crusts have been long neglected and are thin, the Boussingault hot rolls are improved by dipping the crust in water before putting it into the oven. This is not necessary in experimenting with a whole loaf or a thick piece of stale bread. The crumb of bread, whether new or stale, contains about 45% of water. Miller says, the difference in properties between the two depends simply upon the difference in molecular arrangement. This molecular arrangement is the customary modern method of explaining a multitude of similar physical and chemical problems, or, as I would rather say, of evading explanation under the cover of a vague, conventional phrase. I have made some simple experiments which supply a visible explanation of the facts, without invoking the aid of any invisible atoms or molecules, or any imaginary arrangements or rearrangements of these imaginary entities. I find that as bread becomes stale, its porosity appears to increase, and that, when renewed by heating, it returns to its original, apparently smaller degree of porosity. That this change can be only apparent is evident from the facts that the total quantity of solid material in the loaf remains the same, and its total dimensions are retained more or less completely by the rigidity of the crust. I say more or less, because this depends upon the thickness and hardness of the crust, and also upon the completeness of its surrounding. Lightly baked loaves shrink a little in dimensions in becoming stale, and partly regain the loss on reheating, but this difference only exaggerates the apparent paradox of varying porosity, as the diminished bulk of a given quantity of material displays increased porosity, and the increase of total dimensions accompanies the diminished porosity. I have obtained a reconciliation of this paradox by careful examination of the structure of the crumb. This shows that the larger or decidedly visible pores are cells having walls of somewhat silky appearance. The silky luster and structure is, I have no doubt, due to a varnish of dextrin, the gummy nature of which I have already described. On looking a little more closely at this inner surface of the big blowholes, with the aid of a hand lens of moderate power, I find it is not a continuous varnish of gum, but a network, or agglomeration of gummy fibers and particles barely touching each other. My theory of the change that takes place as the bread becomes stale is that these fibers and particles gradually approach each other either by shrinkage or adhesive attraction, and thus consolidate and harden the walls of each by the millions of easily visible pores. These walls forming the solid material of which the loaf is made up. In doing so, they naturally increase the dimensions of the visible pores, while the microscopic interstices, or spaces between the minute fibers of the cell walls, are diminished by the approximation or adhesion of the fibers to each other. This adhesion is probably aided by an oozing out or efflorescence of the vapor held by the fibers and its condensation on their surfaces. This point, be it understood, is merely hypothetical, as the efflorescence is not visible. All the other phenomena I have just described are visible either with the naked eye or by the aid of a lens. When the stale bread is again heated, a general expansion occurs by the conversion of liquid water into aqueous vapor, every grain of water thus converted expanding to 1,700 times its former bulk. As this happens throughout, that is, upon the surface of every one of the countless fibers or particles, there must be a general elbowing in the crowd, breaking up the recent adhesion between these fibers and thrusting them all apart in the directions of least resistance, that is, towards the open spaces of the larger and visible pores, producing that apparent diminution of porosity that I have observed as the easily visible characteristic of the change. This explanation may be further demonstrated by cutting a loaf through the middle from top to bottom and exposing the cut surfaces. In this case, the bread becomes unequally stale, more so near the cut surface than within. The unequal pull, due to the greater approximation and adhesion of the fibers and small particles, causes a rupture of the exposed surface of the crumb, which becomes cracked or fissured without any perceptible alteration of the size of the visible pores. If the two broken faces be now accurately placed together, the halves thus closely joined, firmly tied, and placed for an hour in the oven, it will be seen on separating them that the chasms are considerably closed, though not quite healed. Careful examination of the structure of the inside, by breaking out a portion of the crumb, will reveal that loosening which I have described. Popped corn is a peculiar example of starch cookery. Here a certain degree of porosity is given to an originally close compacted structure of starch by the simple operation of explosive violence, due to the sudden conversion into vapor of the water naturally associated with the starch. The operation is too rapid for the production of much dextrin. End of section 13.